All right, so we are recording now. So no major announcements, just the last few classes. We're just gonna do a bunch of interesting little special topics now. So we've done the Wilkinson power divider, and today we're gonna focus on the quadrature hybrid. Monday we'll do the branch line coupler, and then after that, it's just gonna be a grab bag of whatever fun topics I can dig up in the literature or in the textbooks. So let's just, unless there's any major questions or concerns. Oh, I've got my to-do list here. I was gonna upload a template of some kind just for your research reports. So I kind of had like a bunch of bullet points in the initial syllabus, so I'm gonna maybe do just a little crude Word document, put your title here, describe these things here in these sections, and that's about it. So like I said, I'm not looking for too much in terms of, technical writing quality. Just kind of demonstrate to me that you read the thing, you actually tried to read it sincerely, and you got the gist of it, and you can kind of apply it to broader context. So those are kind of the main things I want to see when I read it. So my goal is to pick up this paper and look through and be like, yep, you read it, and you're explaining to me what it was all about. And if I just walk away feeling like, yep, that's what it sounds like it was all about, and you seem like what you're doing, then you'll get like full credit. Otherwise, like that's my goal. That's what I want to have happen. Right? So,
I have a question for grading breakdown for 6000 course. So in your first class, how you break down the grade, it was total 110 points. So I don't know, so you will grade out of 110 points for 6000 course?
I think the way Canvas is set up is if I assign something to some people but not others, it'll just kind of automatically adjust all that stuff. So the idea was, I think the way I had it in the syllabus was this little report was like 5 or 10% of your final grade, I believe. So if you're in 6000, everything will just sort of automatically adjust the numbers accordingly. And if you're 5000, it just won't necessarily be counted. But I don't know. The exact breakdown will be kind of a question of how many points it is out of your total. So I forget what I put on the syllabus. Was it like 5%?
I can share the screen if you want.
Oh, yeah. If you've got that up in front of you. You should be able to share right now.
Okay. Yeah, here is it.
Yeah. So yeah, that adds up to more than 100%. It just means if you're in 6000 level, that will, yeah, I guess that's a good point. How it's going to it's going to readjust all the numbers, isn't it? So can think of the black numbers in terms of 5000. It adds up to 100. And then I guess everything will just be sort of proportionately adjusted if you're in the 6000 level class. Does that kind of make sense? I didn't quite think that through, did I? So all I know is Canvas will do some kind of automatic adjustments depending on how much credit in proportion to your grade it's worth. So just think about it in those terms. It's going to readjust everything a little bit. So if you're in 6000, yeah, the midterms won't be exactly be 50%. They'll be like 45% of your grade or whatever it's sort of the post-adjustment percentages turn into. Does that make sense?
Yep. Okay. Thank you.
So let's take a look at our kind of practice work for today. So things are gonna get a little bit easier for the next few days. So we're just doing some basic practice problems. So if you watched the lecture, you saw how we did the quadrature hybrid. And I was kind of racking my brain, like what's the difference between a Wilkinson power divider and the quadrature hybrid? And really it's just that 90-degree phase shift at the output ports. So a Wilkinson divider will take a signal, split it into two, and they'll both be perfectly in phase with each other. So not only does it split the power in two, but you have that phase, zero phase offset between them as well. The quadrature is it's doing the same thing. You get a 50% power split, but now all of a sudden they're 90 degrees out of phase with each other. So I'm kind of curious, how many of you have taken something like digital communication theory? Just kind of quick show of hands.
Sorry, repeat the question.
How many of you have taken digital communication theory? I'm just kind of curious. So, okay, I got a few thumbs up there. So you remember the idea of, you had like quadrature amplitude modulation? Was that idea of how, oh, it's been so long since I took that class or had to think about that stuff. But you had that notion of, you had the in phase and quadrature allowed you to kind of cram extra bits into the same bandwidth. But you needed that signal that was 90 degrees out of phase. So this notion of having that 90 degrees phase shift is really important when you're doing digital communication, because you need that in phase and the quadrature carrier signal there. So that's kind of what I was thinking is one of the main applications that occurs to me for that quadrature hybrid, because you need that. So anyway, so the question is just, let's just design a hybrid. Sorry, I need to share my screen again. So design a quadrature hybrid. So 50 ohms, center frequency, and then that sort of propagation velocity. And so it's pretty straightforward once you've got kind of this stuff down, right? So here, I'm going to put this onto the camera here. So you look at that. In fact, here, let's stop sharing again. Just look at the camera real quick. So the picture in the book is pretty straightforward. I kind of like how they represented this microstrip now, because if you were to start drawing this with sort of the schematic, the twin wire schematics for a transmission line, that would look hideous. But all you need to know is two parameters to make a quadrature hybrid. All you need to know is, what is the length here, lambda over 4, and what is the thickness here to achieve that z naught over square root of 2. So if we're making this out of our microstrip, we know that this is going to be like 3 millimeters here to get our 50 ohms. That guy there will be 50 millimeters, 50. And all I need to know is, what do I need to get that 50 over square root of 2? And then, of course, if I pick a center frequency and I know my propagation velocity, then I can figure out how long these strips have to be in order to get that lambda over 4. So we'll just do a quickie little exercise. So let's go back to the screen share. So I just copied and pasted the code I was doing last time. So there's the Wilkinson power stuff that we did before. So I'm going to hang on to that, because the second part of the question was doing the frequency response, which is what I'm going to stick into your homework assignment later. So what did I say? I think I said 2 gigahertz. There's our phase velocity. There's our Z naught is 50 ohms. So the only major change you have to do is divide by square root of 2 for our quadrature hybrid there. And then, like, that's it. You're just one little line of code, and now you know everything you need to know here. So let's copy or comment out that. So we go back over here. So you notice I need about 2 centimeters for the little quadrature bit. Then the only real question is, what are the widths that I'm going to need for those traces there? So let's go back here. I'm just going to open up my lab code. I think it was lab 4. That's where I did this stuff again. So we did this back in lab number 4, where we look at our trusty little chart. There you go. So there's our characteristic impedance as a function of our strip width. Oops, that's phase velocity on graph. There it is. So remember, we did that little intersection point. So the Wilkinson divider, you needed a slightly higher impedance for that little branch bit. So that meant I had to shrink my little strip width down a little bit. So to go to 1 over square root of 2, we have to go in the opposite direction. So you just kind of come over here. So I'm going to take this, instead of multiplying by square root of 2, I'll just divide. So that'll create my little, oops, my little intersection line. Let's have it go all the way out to 10 while we're at it. There we go. Bloop. So you look at that. Oh, okay. 1 over, or 50 divided by square root of 2 is around 35-ish. And you see you need 5 millimeters. And that's basically it. There's your hybrid in a nutshell. to make that thing work. So you would just have, okay, my W1 is going to be about 3 millimeters, and then W2 is about 5 millimeters. So you just consult your table there. Is that right? Yeah, 5.1, okay, something like that. And that's it. That is how you would design a quadrature hybrid for a center frequency of, say, 2 gigahertz. So if we go back here, you'll just say width 1 is about 3 millimeters, width 2 is 5-ish millimeters. And then your length was lambda over 4, which turned out to be about 2 centimeters. And that's basically it. That's how you design it, and you just feed that into some CAD software and let it rip. So then the next question I thought was an interesting exercise. Well, let's do the frequency response of a Wilkinson divider, because we designed it, but the question is, how well will it perform? How much bandwidth is that thing going to have? So what you want to know is the return loss on the thing. So when I say frequency response, what I should have said specifically is return loss, because that's what we care about, right? Normally, you're going to feed energy into port number 1. It's going to split out port number 2 and 3. So the return loss is kind of a measure of how much power is getting into that thing and coming out the other end. So I just said, we'll pick some lengths here. We'll pick a phase velocity and some impedances, and then we just have to calculate S11. So it turns out it's actually very easy to do that for the Wilkinson divider. Also, fun fact, I made a very pitiful attempt to put one of these together yesterday. It didn't work so well, but this is kind of how it should look. So there's my 50 ohm line. There's my, it's really hard to get like exactly 1.5 millimeters with your bare fingers on this stuff. So I tried, and then I put a little 100 ohm resistor here. There's a 50, and then I would put a little 50 ohm and tried to measure return loss on this. It was kind of like this flat minus 10 dB everywhere. It was kind of hideous. So my hunch is just this did not work out so well when I tried to put that together. But you can see in the book, by the way, they have a nice picture of that. So the idea is, 50 ohms comes here. You would just split it off, and you have to just have this little, little resistor kind of bridging right there, and then you'd have your 50 ohms kind of carrying off after the fact. So I tried something like that. It didn't work out so well. It's probably any number of reasons. Could be because I'm trying to use this. I'm not using little chip resistors. That could be one reason. Maybe my strip width is just, you can't really control it that well with your bare fingers, because that has to be 1.5 millimeters. And if you're off by a bit, you get something like 80 or 90 or 60 ohms instead of that 70.7 that you need. So a lot of things can kind of come together to mess that up. And that actually gave me an idea that if we're going to do this sort of thing in the future, what would be really nice is if we found a copper-clad material where you don't need to be so thin on your trace here in order to get, say, 50 to 75 ohms. So the question, an interesting question is, what would I have to do to this copper-clad board? Like increase the dielectric or decrease it, or maybe make it thicker or thinner, such that if I want, say, a 50 ohm line, I don't need this 3 millimeters. Maybe I could get away with a full centimeter. Then it'll be so much more easier to do this sort of lab project with your bare hands. But that's me looking ahead the next semester for the next batch of 3,300 students there. But something to kind of think about, all these parameters that you have control over. So sorry, that was a bit of a tangent. So what we're going to do is calculate the frequency response. So you imagine, here is my trace coming in. So I'm going to do this from sort of like a microstrip perspective. There's 50 ohms here. Sorry, let me gotta move my screen over here so I can see what I'm doing. There we go. And this will branch off kind of like that. And then this guy here, remember, it's going to have a characteristic impedance of 50 times square root of 2. So that's like 70.7 ohms. And then 70.7 ohms there. And then you'll have a resistor that jumps from here to here, which is going to be 100 ohms. And then you go off 50 ohms again. And then you go off again with 50 ohm impedance. So to calculate the frequency response or the return loss, I basically just need to know what is the reflection coefficient looking into this thing, right? So gamma would be V1 minus over V1 plus, and these two guys here are 0. So there's going to be signals leaving like that, but nothing coming in from the other side. So it's interesting, it's actually pretty straightforward to calculate the reflection coefficient, because if I excite it here, that signal is going to, at least in an ideal divider, that signal is going to split equally. I'm going to have a voltage here and a voltage here like that. And I can't really have any net current flowing down this guy. So that was an interesting question, though, is does the physical length from here to here have an effect on the impedance of my divider? So that, because you look at this, they're using this tiny little chip. So ideally, it seems like you don't want any sort of phase delay looking down in there. Otherwise, that'll affect your divider's performance. So I'm kind of curious, does like the physical length here introduce some sort of phase issues that messes with that as well? But in an ideal Wilkinson divider, there is no sort of electrical delay looking up and down here. So I'm kind of curious how that, if that needs to really be compensated for in a real device. But the idea, though, is there's no current flowing here. So essentially all you see looking down into here is 50 ohms of a load with a 70.7 ohm impedance, right? So the question then is, what is the equivalent impedance? So I'm going to use our little red here. Just call that like Z in. What is that input impedance looking down those two lines? And then you'll know that the total net equivalent impedance will just be the parallel combination of the two. So all I need to know is Z in is going to be, we just do the transmission line impedance equation, Z naught, ZL plus J Z naught, tangent of beta L, Z naught plus J ZL, tangent of beta L. So in this particular situation, that Z naught here is actually going to be Z naught times square root of 2, or the 70.7 ohms here, because that's the characteristic impedance looking down this little length of line. And then the load, so that ZL there is just going to be 50 ohms. And this is the thing that's going to vary with frequency. And then, of course, it should ideally be perfectly symmetric. So I know that my equivalent impedance will just be Z in divided by 2. So whatever that number is, that's my equivalent input impedance. And this will, of course, be, you can think of it as a function of frequency, like that. So then my gamma will be Z EQ minus Z naught over Z EQ plus Z naught, where this is now 50 ohms, and that's just whatever we calculate here. So this guy here should be a function of frequency. This guy here will just be a fixed 50 ohms. So that's the idea. And then, of course, this thing here, remember, beta L is going to be 2 pi over lambda times whatever that length is. So you have to pick a center frequency and determine that length. I think I just said, let's fix this at 4 centimeters in the, let's double check that. Yeah, 4 centimeters. So that L is going to be a fixed distance. This lambda now, so finally lambda is, so remember, phase velocity is frequency times lambda, so therefore that lambda is going to be phase velocity over frequency. Okay, so that's, sorry, I should forgot to go back here. There we go. There we go. Sorry, I lost track of myself. So that's what we have to plug in for here. So then that implies beta L is going to be 2 pi f over, beta L, phase velocity times L. Okay, so I now know everything I need to know to shove into MATLAB to get a frequency response out of this. So let's just go ahead and do that. Oops. I almost ended the meeting. I need to screen share it, wrong button. Okay, so let's just go ahead and we'll define some model parameters again. So the length, the branch length, I fixed it to 4e minus 2. That's a fixed value. We know the phase velocity is fixed. The branch impedance there. Okay, so all of this is the hybrid stuff, which we'll just kind of put a little marker here. Let's do something like this, just to kind of demarcate the problems here. There we go. So my Z in, or just call it Z branch, I suppose, is going to be Zx, we'll call that the branch impedance, times Z, we'll say Z naught plus J times tangent of beta L. Now we'll calculate that in a minute, divided by, oops, sorry, that needs to be Zx times that. And we'll do, there we go. So that's going to be the input impedance looking down a branch. But I don't know what this beta L is, so we got to calculate that real quick. So we'll just say beta is 2 times pi. Oh, no, we got to create a frequency. Okay, create a frequency axis for sweep. So we'll just say 1,000 samples. So F. So usually what I kind of like to do is play around with the min and max here, something like that. And then we'll say F is lin space of F min, F max. And so if we don't like our span, we can just kind of toy with these limits a little bit. Okay, and now we know that beta is going to be 2 times pi times F over phase velocity. Then beta L, so I'll just type BL, is beta times L, like that. Did that catch everything? Yeah, 2 pi F over phase velocity. There we go. Okay, and then calculate equivalent input impedance looking down divider. So you just say Zn is just the branch over 2, basically, assuming it's symmetric. And then calculate reflection coefficient. So gamma is just now going to be Zn minus Z naught divided by Zn plus Z naught. Then we calculate return loss. RL is 20 times log 10 of absolute value of gamma. There we go. So if I did everything correct, we should see a nice match somewhere in the vicinity of, oh, actually, what is lambda over 4? I forget what values I put in, but it'll be somewhere around between 500 and 1 gigahertz, I think. I just pulled this sort of number out of thin air. So I don't know exactly what frequency that will correspond to, but it's pretty long length. So I think that's going to probably fall around 500-ish to 1 megahertz to 1,000. So we'll see how that goes. Plot F. We'll divide it by a billion, so we're just going to have units of gigahertz, and then RF. Okay. And then we'll see how that looks. And there you go. Oh, it's right around 1 gigahertz, just like that. So let's do this here. So we'll touch it up a bit, like that. And then we'll say axis helps to do F min, F max, like that. And then we'll go negative, oh, I don't know, 40 and 0. So that's a nice way to kind of think of it. So that's it. So that's what a typical insertion loss or return loss for a Wilkinson power divider ought to look like. And you can kind of see it's in the book, the textbook there too. It gives a nice simpler value. Only they use sort of normalized frequency units. And yeah, okay. Sorry, they also plot all the other S parameters. There's an S12 and an S23 in there as well. But this is all we've cared about for now. So this is what I'm going to kind of ask you to do on the homework eventually when I finish writing it all. So it's going to probably be sometime next week when I post it, and then it'll be the 4th of December when it's actually due. But I will probably just post this little script file to show you how that works. And then you just, of course, have to touch it up. So you'll say something like X label. Oops. So you say frequency, and it's gigahertz. Y label, return loss. And you say dB. Technically, decibels are not a unit, but I think it's helpful to kind of treat it as such, and you can sort of treat it like a unit. But there you go. So let's let that go out a little bit more. Let's say out to 2.5. And you'll notice if you go way, way out, you get another dip again. So that's because that branch, that quarter wavelength, technically it'll also work at like 5 quarter wavelengths and 9 quarter wavelengths, right? So as you go way up in frequency, you keep getting these extra matches again, because you're sort of going around. You can think of it as just doing a complete circle around the Smith chart kind of thing. But anyway, so that is everything you need to know about a Wilkinson power divider. We could also have calculated the input impedance, or sort of like looking from port 2 into port 3 and that kind of stuff. I don't know if there's really that much call for that. In my experience, this is all I've ever really needed to use it for, is you're feeding it into one port and you want it to split into 2. So you know that if you're matched, you're getting a good even split, assuming you're, but you could validate that by using a network analyzer as well. So I think that was all I really had for today. The last little thought I had was like we could do some of the derivation, but yeah, I didn't want to waste too much effort. I was thinking I'll do that as a homework problem, because if you watch the hybrid coupler, we went through the even mode analysis, and I just sort of skipped the odd, saying here's the results you get. So I was thinking that would be a good kind of homework assignment. Now that you've seen it several times, you should be able to kind of do it yourself, where you calculate the ABCD matrix, you multiply them all together, and that'll tell you the signal sort of coming out the other end, and then you can use that stuff to derive all the other parameters you need. So I'm thinking we'll make that a homework problem as well. But that's pretty much all I had for today. So we designed the quadrature hybrid, and we did a frequency response on a Wilkinson power divider. So both of those will be short little homework problems later next week when I post it. Okay. No questions or comments? And otherwise, you're free to go. Just go ahead and submit something like that for your attendance credit, and that's it. So thank you for joining.
I got a quick question.
Mm-hmm.
How many of the class plans on taking microwave engineering 2?
Oh, that's a good question. Oh, thank you for reminding. Dr. First has been asking me to advertise for Microwave 2 next semester, and she needs at least 6 students to enroll in it in order to offer the class. So how many students here feel confident enough to take Microwave number 2 from Dr. First next semester?
I have a question about microwaves number 2. When I read basically what it goes over and what it's taught, it seems like it's pretty much rehashing what we're doing in RF analog design with the transistor level and things like that.
Mm-hmm.
Is there a huge difference between the 2 classes, or is it going to be like if I took microwaves 2, it's just going to be a rehash of this semester with maybe a few little things thrown in?
I wouldn't trust too much on the online stuff, because there was barely 2 weeks ago a discussion from the EM committee to revise all of that, because there was a lot of weird overlap and stuff that was supposedly going to be taught in this class that's supposed to actually be taught in the next class, that kind of thing. So it's hard to say, but I wouldn't put too much stock in whatever you read online. That's being updated soon, if it hasn't already. But just a show of hands, or maybe in the chat. Here, let me go to the gallery view. I don't know how many we actually answered, but how many are intending to take? Oh, half the class already left. So who's intending to take Microwave 2 next semester? So I got one. I know, Corey, you're interested. Nobody else? Or is everybody else just asleep? You're thinking about it? Okay. Okay, we got a possible. I think Cindy said she also is tempted to make it so that you don't actually need this class to take Microwave 2. Because the classes are kind of very separate from each other. Like all the waveguide stuff, it's this nice little self-contained thing, which you don't really need when you do Microwave 2. The first section, remember, was kind of a giant rehash of 3300 anyway. And this last stuff, notice is just a lot of kind of special topics. Here's a Wilkinson divider, here's a quadrature, and that kind of thing, which is great stuff, but it's not like a prerequisite for any of the material later on. So really, like, the only thing you need from this class, if you're going to take Microwave 2, is like the network theory, which she was probably just going to post a few, tutorials to some of the lectures I've done and just say, here, take a few hours and go over this stuff. This is what you'll really be needing. But definitely when you do Microwave 2, you're going to do a lot of like signal noise analysis and amplifier design, amplifier matching, that kind of thing. And what else is there? I don't know.
Is there a lab attached?
Say what?
Is there a lab?
No, there is not. I don't think there's a lab there, just because it's all online and we're not set up to I don't know. It's somebody would have to devise a bunch of labs over that. So Cindy decided to not do any labs. It's all just going to be kind of theory. So I think you do mixers. That's another really interesting bit. You'll do microwave filters. I know that. So yeah, you don't really need this class in order to go into Microwave 2. It'll kind of help, but you could kind of get yourself up to speed pretty quickly. Yeah, because that's where a lot of it, yeah, it's going to be kind of like the classes now. Like today we're doing the Wilkinson divider. Now we're doing this hybrid thing. It's going to be a lot of like that. Today we're going to do microwave amplifiers. We're going to do some matching noise analysis, and then you're going to jump in and do, here's what a mixer is, that kind of stuff. So for what it's worth, you don't need this class, or you don't need to have done super well in this class to do well in that class. But half the students left, so I don't have a complete sample. At least looks like we've got 2 definites plus a couple of maybes. So we'll see how things go next semester. But I guess that's it for the day, so I'm going to stop recording.